Now that you've had some time to get to know rational functions, we're going to keep the equal sign but switch over to rational equations and look at how to solve those. We're also going to look at rational inequalities, the less than, greater than situations. So some of the things you had to consider when you were working with rational functions, you also have to consider when you're working with rational equations. You have fractions where you have variables in the denominator, and you have to make sure that the denominator is never zero. So we have to, as we're solving these equations, we have to go through and figure out, well, what values would make the bottom zero and make sure those are never our solutions. If we happen to get those numbers as solutions, we have to toss them out. They're considered to be extraneous, extra solutions that don't work here. Then as we solve the equations, just like with linear equations that have fractions, we can eliminate the fractions, make our lives easier, by multiplying both sides of the equation by the least common denominator. And this will give you a resulting equation does not have fractions in it and that you can solve. But that very process of multiplying by that least common denominator can mask or hide some of those extraneous solutions. You come up with these solutions that don't really work in the original equation, but they work in that resulting equation. So you got to check. You got to go back, make sure anything that would have made the bottom zero, toss it out. And then to be extra careful, take your solutions that are left and plug them into the original equation, make sure they work. Checking is always a wise thing to do. Okay, so let's do an example so that you can see how this goes down. All right, put up my pen. Excuse me. Okay, let's say we have an equation like this one. 2 over x squared minus 2x minus 3 over x squared minus x. That whole thing equals 0. Okay, and our job here is to solve for x. In this particular equation, x is only found in denominators of fractions. So we have to be really careful how we proceed. So I'm going to first make things a little easier on myself by factoring those denominators. I see a common factor of x in that first denominator. So x squared minus 2x can factor into x times x minus 2. And then I also see a common factor of x in the second denominator. And then x factors out, and then I'm left with x minus 1 as the other factor. All right, I got to make sure each of these denominators never equals 0. So I got to make sure that x times x minus 2 is not 0. So that means x can't be 0, x can't be 2, because 2 minus 2 here would be 0. Also, I got to make sure that x times x minus 1 is not 0. So x can't be 0 again, and x can't be 1, because 1 minus 1 here would be 0. So those are the values I know that I can't have as my final answer. So that's just something to kind of keep to the side and then refer back to it once I finish solving this equation. All right, then to get down to the business of solving the equation, I'm going to make it easier on myself by eliminating fractions. The first fraction in the denominator has factors of x and x minus 2. Second fraction has in the denominator a factor of x, which we've already got an factor of x in our LCD so far, but it also has an x minus 1. So all the different factors from the denominator make up the LCD. On the right side, we just have zeros, so don't worry about it over there. All right, so let's take that LCD. Let's multiply the entire equation by it. All right, so we multiply the first part of the equation, first term here by it. The x and the x minus 2 will cancel out, and that'll leave us with 2 times x minus 1. We multiply second part. We have minus 3. The x and the x minus 1 cancel out, so we just have times x minus 2. We multiply it by this part, we just get 0. And there you go. The resulting equation is a linear equation in one variable. You can go ahead and solve this. And any solutions to the original equation will be found here. But it's also possible you could get some extra solutions that work in this linear equation, but don't necessarily work up here in the rational equation. So that's why it's important to go back and look at your answers, check it out, make sure that you only keep the ones that'll work in the original equation. Okay, so let's solve. Distribute your 2, distribute your minus 3. Okay, 2x minus 3x is negative x. Minus 2 and plus 6 is plus 4. Just add x to both sides. X equals 4. All right, looking up here, none of those values were 4. So that's good. That means I'm safe. That means 4 is a safe solution. It's not going to be extraneous because it's not anything that would ever make the denominators 0 in the original equation. But because I'm a thorough student, I'm still going to plug 4 back into the original equation and make sure it works. And this way I can catch any mistakes I might have made. Checking is very important. So I'm going back to the original equation, plugging in 4 everywhere I see x, and then using order of operations to simplify. Okay, reduce the fractions. Oh goody, I do end up with 0 on both sides. So it checks out. 4 works. So 4 is, the solution set contains 4. So 4 is that magic value of x that makes this original statement true. All right, so I had no extraneous solutions to toss out in that one. And that's basically how you're going to solve these rational equations. All right, I wanted to do another example with you before moving on to the inequalities. Okay, this one looks like this. 2x, this time x is also in the numerator, 2x over x minus 3 plus 4 over x minus 6 equals 0. 2x over x minus 3 plus 4 over x minus 6 equals 0. First things first, let's take these denominators, make sure we identify what would make them 0 so that later we know not to keep those values as solutions. Okay, so we can't have x be 3, we can't have x be 0. Just something to keep in mind for later. Later on, we'll check back there. All right, LCD. First fraction has x minus 3, and that's as simplified, that's as factored as you get. And the second fraction has an x in the denominator. Then over here, minus 6 is like saying minus 6 over 1. So if we take all the different factors from the denominators and multiply them together, that's our least common denominator. So x minus 3 times x. And then we can take that least common denominator and multiply the equation by it to help us eliminate the fractions, which will give us an equation that we can solve to get any solutions that this equation has. But we could also end up, in this process, introducing extra solutions. So that's why we have to be careful. Okay, when we distribute to the 2x over x minus 3, the x minus 3's are going to reduce, leaving us with 2x times x. When we distribute to the plus 4 over x, the x's are going to reduce, leaving us with 4 times x minus 3. When we distribute to the minus 6, there's not going to be any reducing because there's no minus 6 is just minus 6, or you can say 6 over 1. And then when you times by 0, you're going to get 0. All right. So we've got 2x squared plus 4x minus 12 minus 6x. Ooh. Ooh, we got to distribute there. Let's distribute these two first. X times x minus 3, that's going to be x squared minus 3x. So distribute the minus 6x squared plus 18x. I feel like that was easier. So we got a nice quadratic equation. You guys have solved a few of those now. Let's see here. I could factor out a -2. I don't know if that's going to help me. I don't know if this is going to be factorable or what. Right? I haven't really looked that closely yet. 2 times 6 is 12. Factors of 12. Factors of positive 12 to add to a -11. Not happening. So not factorable. So we're going to need to use the quadratic formula on 2x squared minus 11x plus 6 equals 0. Where a is 2, b is -11, c is 6. Okay. So we are going to come up here. X equals -b plus or minus square root b squared minus 4ac all of 2a. Alright, so x equals 11 plus or minus square root 121 minus 4 times 2 is 8, 8 times 6 is 48, all over 4. So x equals 11 plus or minus square root of 73, all over 4. All right, yes, those numbers there, 11 plus the square root of 73 over 4 and 11 minus square root of 73 over 4, neither one of those is 0 or 3. So we're safe. These two solutions are safe. And each one of those, when plugged back into the original equation, will work. I would say use your calculator, make it easier on yourselves. Take 11 plus square root of 73 over 4. Just use the decimal approximation. Plug it into the equation. Make sure it works. Use your calculators. Same thing with 11 minus square root of 73 over 4. It's easier that way. I mean, you could use the square root and keep it that way too, and it'll work, but let's make it easier on yourselves for your check. But I have the answers in front of me here, and those two are correct. And I know I don't have to throw them out because they don't equal 0 or 3, which were the two forbidden numbers. All right, there you go. So 2 examples of how to solve these equations. But that's not all, folks. You also have to solve the inequalities. You got to be able to do it analytically, and you also need to be able to interpret graphs, interpret it graphically, and figure out the solutions for the inequalities. All right, when we go to solve the inequalities, it's a little easier to get everything to the same side first. So that one side's 0, just makes your life a lot easier that way. And then it makes it easier too if you go ahead and combine everything on that side without 0 and make it into one fraction. Because then you can quickly see where this fraction is going to equal 0 and where it's going to be undefined. Where it equals 0 will be your solutions to the equation. Where it's undefined will be your vertical asymptotes. And what you have to do for your inequality is look at what the behavior is on either side of the places where it equals 0, which is where it crosses the x-axis, and either side of the vertical asymptotes. Because on each side of the vertical asymptote, it can be doing different things. If you're trying to solve greater than 0, if you end up with if you have a question where you end up with y1 is greater than 0 or greater than equal to 0, you're trying to basically see where is the graph above the x-axis. And if you end up with less than 0, trying to see, well, where is it below the x-axis? Because equals 0, that's where it crosses the x-axis. That's the x-intercepts. So once you determine where the x-intercepts are, you're looking at, okay, that's where it crosses, but then you have to figure out, well, where is it above? Where is it positive? Where is this expression positive? That's going to be where the graph's above the x-axis. That's the solutions for y1 greater than 0. And then when it's negative, that's the solutions for below the x-axis. So since the behavior can change, since it can change from above to below or below to above at points at the x-intercepts or even on either side of a vertical asymptote, you're going to use the values for where the numerator equaled 0 and where the denominator equaled 0. And you're going to set up a sign chart. And you're going to look at, well, what are the signs, positive or negative, on either side of each of those points? And that will help you to figure out what's going on with the inequality. To help you figure out what intervals go with greater than 0 and what intervals go with less than 0. If you're looking at endpoints for greater than or less than, you're definitely going to use parentheses. If you're looking at greater than equal to or less than equal to, you're going to use brackets. And then if you're looking at the values that make the denominator 0, then you definitely use parentheses there because you can't ever include those numbers as part of your solutions. Okay, so let's translate this a little further. Let's say we start with something like 4 over x plus 1 is less than 2 over x plus 3. Okay, so what we want to do is make sure everything's on the same side. So I'm going to go ahead and subtract 2 over x plus 3 from both sides. So we're trying to get 0 on one side. And it's much easier to me if 0 is over here on the right. So I'm going to go and subtract 2 over x plus 3, 2 over x plus 3 from both sides. All right, now before I can combine these two fractions, I do have to have a common denominator. So in the first fraction, 4 over x plus 1, the denominator has x plus 1, but it doesn't have x plus 3 like this fraction does. So I'm going to times the top and bottom by x plus 3. Then the second fraction has x plus 3 in the denominator. It doesn't have a factor of x plus 1 like that fraction does. So I got to multiply top and bottom by x plus 1. All right. And this is perfectly legal to do as long as x is never negative 1 and x is never negative 3. As long as that never happens. Because negative 1 would make the bottom of this 0 and negative 3 would make the bottom of that 0. But otherwise, any other values are fine. So essentially you're multiplying this first fraction by 1 because x plus 3 over x plus 3 is really 1. And you're multiplying the second fraction by 1 because x plus 1 over x plus 1 is 1. So this is perfectly legal to do. Okay, so numerator of, you end up with 4x plus 12 over x plus 1 times x plus 3. And you're subtracting You got minus 2 times x plus 1 right there. So you're subtracting. Let me put my eraser somewhere. I don't like my eraser. I need to erase that for a second. All right, so then you're subtracting 2x plus 2 over x plus 1 times x plus 3. So you have 4x plus 12. Then don't forget to distribute your minus sign. Minus 2x minus 2 over x plus 1 times x plus 3. So you have 2x plus 10 over x plus 1 times x plus 3. And this is still less than 0. All right. So now, where 2x plus 10 equals 0 would give us our x-intercepts. So that would be at x equals negative 5. And then where x plus 1 times x plus 3 equals 0, that would give us our vertical asymptotes. So that would be at negative 1 and negative 3. So your behavior can change depending on which side of those you're on. That was a really bad start to my drawings. Let me erase that. Okay, so looking at the number line, like we have 0 here, we have negative 1, negative 3, negative 5. You're interested in seeing differences in behavior and the intervals that of the number line that these three separate the number line into. And we're going this direction's negative infinity, going that direction's infinity. So these values separate the number line into an interval with negative infinity, negative 5. Let's see, we're only doing less than, so we're going to use parentheses. Also an interval from negative 5 to negative 3. An interval from negative 3 to negative 1. And an interval from negative 1 to infinity. Because you have these three values here. Negative 5 makes the top 0. Negative 3 and negative 1 make the bottom 0. All right, so what we're going to do is we're going to take each interval and we're going to pick a test point. I'm going to plug it in and see what happens. So I'm going to pick maybe negative 6 out of this interval, negative 4, negative 2, and 0. Okay, and I'm going to go back and plug it into here. All right, if I plug in negative 6, I get negative over positive, so that's negative. If I plug in negative 4, that's positive over positive, so we're talking positive. I plug in negative 2, that's positive over negative, so we're talking negative. And if I plug in 0, Positive over positive is positive. All right. And we were interested in where it's less than 0. So we're interested in the negatives. It's negative at negative infinity to negative 5, so any values in that interval. It's also negative in the interval from negative 3 to negative 1. So there's your solution. If you needed to see where it was greater than 0, then that would be the positive intervals. Negative 5 to negative 3, union negative 1 to infinity. Y1 equals 0 at negative 5. And a little more clarification, if you needed to know where y1 was less than or equal to 0, you would need to include the negative 5, because that's where it equals 0. So you would put bracket around negative 5. Infinities always have parentheses, and the negative 3 and the negative 1 in this case would have parentheses, because those are where the vertical asymptotes are. It's never going to take on those values. If it asks greater than or equal to 0, it would look like this. So that's a little bit of clarification on how that works. All right, so there's a full example of an inequality. Let me do one kind of special case one with you real quick. Okay. For this problem, they give you first 7 over x plus 2 equals 1 over x plus 2. Then they give you 7 over x plus 2 is greater than or equal to 1 over x plus 2. And then they give you 7 over x plus 2 is less than or equal to 1 over x plus 2. All right, for the equals, like if you go ahead and subtract 1 over x plus 2 from both sides, you're going to get 6 over x plus 2 equals 0. This never happens. Because in order for it to equal 0, your numerator would have to be 0. And its numerator is just plain old 6. There's no variable up there. So it's not possible. There are no values of x that'll make this happen. So the solution set is empty. But we can still work on the inequalities because you do have the fact that x plus 2 can't be 0. So you do have a vertical asymptote, and you can observe and see what the behavior is on either side of your vertical asymptote. So what's happening below negative 2 and what's happening above negative 2. Negative 2 is always going to have parentheses on it because that's where the vertical asymptote is. So let's pick the test points. Let's see, if we plug in negative 3, we're going to get positive over negative, which is negative. If we plug in 0, we're going to have positive over positive, which is positive. All right, so for the greater than or equal to, that's the positive. That's going to be from negative 2 to infinity. And for the less than or equal to, that's going to be the negative infinity to negative 2. So even though we don't have anywhere where it equals 0, we do have, apparently, the graph is above the x-axis from after negative 2, and it's below the x-axis before negative 2. So the vertical asymptote is kind of that dividing line of where the graph's below the x-axis and where the graph's above the x-axis. So apparently, y equals 0 is a horizontal asymptote. All right. So I have a slide about using the calculator. So let's go ahead and do that. Let's use some of the two of the same problems, and let's put them in the calculator and see how this looks. Like let's just go ahead and put in in this problem here, let's put in the 2x plus 10 over x plus 1 times x plus 3. Okay, let's hit graph. All right, and when we had done our values, we'd seen that it equaled, that the x-intercept was at -5. So that would be right here. 1, 2, 3, 4, 5. There's the x-intercept. It also showed the vertical asymptotes were at x equals -1 and x equals -3. So x equals -1, there's your vertical asymptote right there. And x equals -3, there's your vertical asymptote. And in the graph, what we're seeing is that the graph is below the x-axis from way out here to -infinity until the graph crosses the x-axis at -5. So for the less than 0, trying to see how to move that around. For the less than 0, from -infinity to -5, the graph's below the x-axis. Then the graph's above the x-axis from -5 until you get to your vertical asymptote at -3. And it's below the x-axis between the vertical asymptotes of -3 and -1. So the less than 0 includes -3 to -1. Greater than 0, it's above the x-axis after -5 up to the vertical asymptote at -3, but it doesn't touch -3. It's also above the x-axis after the vertical asymptote at -1, and it continues to be above the x-axis from there on out to infinity. There's a horizontal asymptote there at y equals 0, so out to infinity, the graph's getting closer and closer, but doesn't touch it. So there are no more x-intercepts. In the horizontal asymptote, the graph can cross it, but you're going to see that it tends to stay kind of a pattern nearby. So even this piece of the graph, it crosses the horizontal asymptote, but at -5, but it still kind of stays close. It hugs it. So at least that gives you a trend. But a vertical asymptote graph will never cross. So there's graphically what's happening to that problem. And then to this problem, let's see here, 6 over x plus 2. Oops, looks like I mistyped that, sorry. Let's delete that extra x there. Definitely a different looking graph. Okay, here we go. So this graph, the vertical asymptote at -2, that makes sense because here's -2. Graph, you could tell, like split. To the left of -2, the graph's below the x-axis. To the right of -2, the graph's above the x-axis. That's right in line with what we found. Does not touch the x-axis, so there's no solution where it equals 0. Greater than or equal to 0 is above the x-axis, and that's after -2. That's this part. And then less than or equal to 0 is below the x-axis. That's before -2. That's this part. So graphically supports what we found analytically. Analytically is when we worked it out like this, so like I did on the slide. Graphically is graphing it and seeing what the picture tells us. All right. One more thing. I just wanted to do a quick word problem with you guys. Quick word problem. It says, suppose that the population of a species of fish in thousands is modeled by, Why does it always change the color back? I need to figure out how to change the default color. All right. You have a species of fish where they've modeled the population with this function. F of x equals x plus 10 over 0.5x squared plus 1. Okay. And x is greater than or equal to 0, so you're not going to have any kind of negatives. And the x is our years. You're not going to have negative years, so that makes sense. You can have 0 years or positive years, but not negative. So however many years have passed, you put them in for x, and the result this spits out, the f of x, will be the population of this species of fish in thousands. So f of x is population of a species of fish in thousands. Okay. So what we're going to do is we're going to use our calculators and we're going to graph this. We're going to graph and we're going to use a window of 0 to 12 by 0 to 12. So let's do that. So we got to graph x plus 10. I like putting the numerator in parentheses. I also like putting the denominator in parentheses, just to make sure to force the calculator to do the correct order of operations. All right, x plus, I don't know what's going on with my mouse, but it keeps double doing things. All right, x plus 10 divided by, that's why it's always important to go back and check your input, 0.5x squared plus 1. All right, that's the graph. Right now, if I don't set the window, this is what the graph looks like. But remember, it doesn't make sense to have this with negative x, because x is in years. X is going to be 0 or higher. So we're going to ignore this side of the graph. So we're going to adjust our window. We're going to go to window, which is right here next to y equals. And they told us to use 0 to 12. And I'll just keep the scale at 1. 0 to 12, 0 to 12. So then that'll refine the graph and just focus on the part we care about. So at x equals 0, the graph starts here at the on the y-axis, and then it's kind of a downhill slope. And it continues to be downhill, and it starts to flatten out. Gets closer and closer to the x-axis, but doesn't actually touch it. All right, so we're interested in the initial population. Well, I could count this and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and say, well, that's pretty close to 10. But I don't know if it's exactly at 10. So right now, 10,000 fish. Remember, this is in thousands. The output's in thousands. So 10,000 fish is a good estimate. But I really do want to see exactly how much it is. But I can go to table, which is second graph, and I can look up what's happening at x equals 0 right there. At x equals 0, y is 10. And that's in thousands. So yes, the initial population is 10,000 fish. What happens to the population after many years? Well, you can see it in your graph. The population's getting lower and lower. It's disappearing. So the species is dying out. That's not good. Might have, looks like we're heading towards, over time, you're heading towards an extinction event for that species. Interpret the horizontal asymptote. Well, the horizontal asymptote looks like it's at y equals 0. So this graph tends towards 0. Whether or not it crosses 0 later on, in real life, that's something to tell. Right now, this particular graph doesn't actually cross 0, But in real life, you can have an extinction event where you hit 0 and that's it. You don't have any more of that species of fish. So based on our graph, I can go ahead and say that we have this graph here. Looks like this. And at x equals 0, y is 10. So the initial population of the fish is 10,000. We have a horizontal asymptote at y equals 0, which if you just look at your original function, you can tell that. Original function, you have a degree of 1 in the numerator, degree of 2 in the denominator. So the degree in the numerator is smaller than the degree in the denominator. So that tells us we have a horizontal asymptote at y equals 0. So the fish species is dying out over time. So that's where the biologists are going to say, okay, we got to do something about this, because if we wait too long, they're going to be gone. Population tends towards 0. So that's an example of a rational function and how you can, think about it like a rational equation when you're looking at, initial population. That's where x is 0. You're trying to see what y equals. And you're trying to figure out, well, over time, where does this function end up equaling 0? Well, it's not, according to that function, it's not going to equal 0, but it tends towards 0. But in real life, yeah, you're going to interpret that and say, yeah, it's going to eventually be 0 if things keep going the way they're going. Okay, so there you go. So there's some rational equations, rational inequalities. Have lots of fun with those. Always check your solutions. Make sure the ones you have are going to stick. Make sure they're not going to cause the bottom to be 0. Not going to have any kind of vertical, like your vertical asymptotes. You got to watch and make sure you don't say that x equals any of those values. All right. Well, thank you for joining us. And next time we're going to dive further into powers and roots, have some more fun, and go from there.